Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Inoh Kembali bin Zulkifli, and today for this presentation I will talk on the technical paper review for seismic wave interpretation. My title is Anisotrophy migration. So this is the outline for today's presentation. First is the introduction. Next I will move on to the problem statement and the objective. I will also talk on the application. And then we will gonna look on the literature review that I found, and lastly I will do the conclusion. So what is the anisotrophy? Anisotrophy is defined as the variation in physical properties depend upon the direction in which it is measured. Basically all the Earth's structure will have its own variation, and this variation mainly caused by the first we have aligned mineral grains, then we have aligned fracture, aligned crystal, and a periodic thin layer. And so for this seismic hydrotrophy is usually common in the sedimentary rock and shale. So this is the problem statement that I found for this topic. Since seismic hydrotrophy is the variation of velocity with direction, usually this phenomena will have the, effects on the time to depth conversion of seismic data. This will result in the incorrect image of the subsurface structure. It also repositions the reflecting event to a more accurate representation of the true superficial relationship when we're doing the depth imaging. So this misinterpretation can seriously alter the location of our exploration target, mainly if we do the for the exploration purpose. And the anisotropy also has effects on the shale physical properties, such as composition, microstructure, or clay, to the seismic characteristics that hard to evaluate. So this is the objective. Mainly we have only two objectives here. First of all is to describe the layer geometry and the detailed velocity information of the subsurface. And lastly, we want to illustrate different case study of this anisotropy migration. This is the application where we use this anisotropy. So most of the seismic anisotropy studies involve three things, which is the theoretical aspect, studying anisotropy in the flat lying back, or using shear wave anisotropy in the fracture detection. And this anisotropy is also usually used in the depth imaging of in structural environment. The most common one is the trussbed or subsalt imaging. Now we will move on to the literature review that I found when doing this technical paper review. So this is the first case study. We have here is the anisotropic pre-stack depth migration. For this case study, they use a physical model, as you can see in the figure. So this model mimic the structure found in the central Alberta foothill. So for this model, they will produce two results. The first result is the isotropic pre-stack depth migration, and the second result is the anisotropic pre-stack depth migration. So from these two results, they will compare which one can correctly migrate the data from this physical model. So for this first result, the data was migrated isotropically with a velocity model that built using the constant fast velocity of the truss sheets and its actual spatial location for the migration. So as you can see in the figure, which is the result, the arrows indicate that the true depth position of the basal reflector. Although the continuity of the basal is quite good, however, it is located too far in depth under the truss sheet. Here we have the sampling of depth getter, which result from the migration figure as shown in a figure above. So note that the near offset are at the right side of each getter and far offset at the left. In addition, the depth getter identification indicates that the migration velocity is too low and should be increased. However, if doing so, the reflector can be pushed even farther from the depth, which is incorrect. So for this result, it shows the anisotropic pre-stack depth migration using the correct parameter of the physical model. So note that the basal reflector is allocated in the correct depth location under the truss sheet, and the residual structure in the reflector interest has been eliminated. This shows that the anisotropic pre-stack depth migration is the only way to eliminate the discrepancy between the correct depth and the residual move out the image scatter. And the figures that shows the correct depth image of the original model, and the reflector continuity is maintained, which is also correctly located in depth, and the event within the depth getter are flattened. So this is the figures of the sampling of depth getter result from the migration on the figure above. It should be noted that the small amount of residual move out in the depth getter is associated with the precision model building process. Therefore, overall, in this study, it has been demonstrated that isotropic pre-step depth migration is limited in its ability to correctly migrate data from the anisotropic physical model. It is because it leads to the discrepancy between the correct reflected depth and the residual move out in the image scatter. This is the second case study that I'm going to present. It is the physical model study of shield seismic response and the anisotropic inversion. So on the figure here we have two lines of a different group. So for line 1 we have a group S that contain 6 shield block with different clay content, and then we have line 2, which is group N, contain 6 shield block also but with a different porosity. So the objective for this study is to know the seismic response of the clearish shale and know the estimation of the shale elastic properties. And before we going through this result, note that uh, all these results are only focusing on the line 1, which is the shale block with a different clay content. So in the figure here we have the anisotropy 3-term inversion method. So this A, it shows the acoustic impedance for the shale block with a different clay content, while on the figure B it shows the shear modulus result, and in the figure C it shows the inverted horizontal P wave velocity. So for this model, actually only the figure in A has shown the significantly effects on the clay properties comparing to the other two figures. So this figure shows the second result, which is the isotropic inversion. However, this result represent less accuracy compared to the result that being shown before, which is the 3-term inversion result. So here we have the third result. For this inverse P-wave anisotropy parameter, we can see that it high in block S5 and in block S6 also. We show there's high clay content there, and it is low in the blocks with low clay content. So through this result, we can see that it is highly agree with the measured P-wave anisotropy before. And then overall for this case study, what I could say is the inversion result really indicate that the anisotropic 3-term inversion method before that I shown could also provide the accurate result as well as this P-wave anisotropy for the elastic properties of the shale formation as in the objective. In the conclusion, anisotropic migration is required to properly process the seismic data in order for us to have the correct result of the subsurface. This shows that the anisotropic migration provides a new shift in the seismic imaging. And then this anisotropy are also able to identify the elastic properties of shale as shown in the case study number 2. And then this anisotropy is also an important migration algorithm which able to create the highly accurate model of the subsurface in the future. So last but not least is this is my reference that I use when producing this technical paper review. So with that, I think thank you for listening to my presentation and have a good day ahead.